Yesterday we learned that a collision involving two objects at right angles, sometimes they call that a T-bone collision, is really just the same thing as two different collisions that we've already analyzed. This collision that you see on the left-hand side is the same as this collision where object number one is moving towards a stationary object number two, and this collision where object number two is moving downwards towards a stationary object number one. We know how to analyze this collision. This is all on the x-axis, and we know how to do this. We know how to analyze this collision. It's all on the y-axis. We know how to do it. So all I'm asking you to do for this collision, where we have both of these combined, is to separate the combination, to separate the T-bone collision, the collision at an intersection question, into a horizontal problem that we've already done and a vertical problem that we've also already done. We call those two problems that we've already done our x component and our y component. So when you see one of those questions, just don't try to overanalyze, try to simplify it. You've got a question that looks challenging because you've got two dimensions involved, then separate it into an x component and a y component. And then you're going to have to recombine them, but we'll worry about that later on. Separate them into two separate problems that you know how to solve, and then we'll worry about recombining them. When you're analyzing the x component, if I'm analyzing this problem right here, I'm not paying any attention to this one. So if I'm analyzing the x component of this problem, then I'm not going to pay any attention to the y component. Similarly, when I'm analyzing the y component, I'm going to ignore any x component. When I'm analyzing this problem over here, I'm not paying any attention to this separate problem right here. So I'm analyzing this problem, the y component of this problem. Why would I pay any attention to the x component? When analyzing the x component, ignore the y. When analyzing the y components, ignore the x components. What do you got to do though? What do you got to do after you've analyzed the x and the y components? Then you got to recombine them. And you guys know how to recombine them. We've done that a million times in Physics 20. Once you've got an x final velocity and a y final velocity, then draw a vector diagram. Join the start to the finish. That's the hypotenuse of your triangle, and solve for it. You're going to solve for that resultant velocity, that final velocity, the combination of the x and the y that we just separated by using the Pythagorean theorem. And we're going to solve for the angle by using the tan function, a little bit of trigonometry, almost always going to be the tan function. So if this is pi equals pf, and this is pi equals pf, do pi equals pf and pi equals pf twice for this one. Get an answer right here, get an answer right here, or take this question, get an answer, and then recombine them. Do the Pythagorean theorem and the inverse tan function. Here's our first example. It says a 90-kilogram quarterback moving at 7 meters per second at 270 degrees. We'll deal with that angle in a second, okay? Clearly it's showing direction, but we'll deal with what that means in a second here. That's tackled by a 110-kilogram linebacker running at 8 meters per second at 0 degrees. Right, Chase? What's the velocity of the center of mass of the combination of the two players immediately after impact? So there's a couple issues that we have here besides the two-dimensional nature of this collision. One is that we're not sure exactly what the 270 and the 0 degrees means. Two, what's this whole deal with the center of mass? I have a mass of about 70 kilograms. My mass is distributed not evenly, but unevenly over my entire body. If I'm analyzing my body as part of a physics problem, then I can consider my mass to be concentrated in one place, my center of mass. My center of mass would be somewhere around my belly button. It varies depending upon the person, okay? Some people are a little bit higher than the belly button, some people a little bit lower than the belly button. But generally it's around that spot. The center of mass is where your mass can be considered to be concentrated. We're going to say in this question that although these two football players don't entangle after the collision like we've seen a lot of times, we can assume, we can pretend that they do, because we're looking for the velocity of the center of mass. Okay, we're looking for the velocity of that one spot where both of their masses can be considered to be concentrated. So let's just assume they're two billiard balls, hit each other, stick together, and go off as one object. Okay, that'll work for us. Now, the other thing that we got to think about here is the direction. We're not real familiar with this frame of reference here. This is 0 degrees, this is 90, this is 180 degrees, this is 270 degrees. This could be 0 degrees, or you could go back to 360 degrees. So if you've got a 270 degree angle, that means it's going this way. If you've got a 0 degree angle, it means it's going this way. When you encounter one of these two-dimensional collision problems, and once you recognize that it is a collision, it is conservation of momentum, and it is an XY problem, then my suggestion for writing down your givens is to draw a picture. I got a 90 kilogram quarterback going this way. We'll call him object number 1, and we'll make his velocity 7 meters per second. We've got another object going at 0 degrees. We'll call him object number 2. His mass is 110 kilograms, and his velocity is 8 meters per second. Now, it doesn't say that they go off together as one object, but since we're looking for the center of mass, again, we can assume, we can pretend that they do go off as one object. Okay, one guy goes off this way maybe, one guy goes off this way, but combined, it's as if they're going off somewhere in between. That's what we're looking for. All right, clearly there's motion on both axes, both the x and the y axis. So we've got to break this into our two problems, our x problem and our y problem. And we're going to say pi equals pf for both of them. We're going to say m1 v1i plus m2 v2i equals, and again, we're pretending they stick together so that we can find the velocity of the center of mass, mvf. M1 is 90 kilograms. Can you tell me what v1i is here? Remember, I'm not doing the y component yet. I'm just dealing with x right now, one at a time. Tell me what v1i is. How fast is object number 1 moving? Yep, 0. Good. When analyzing the x component, ignore everything y component. So we're going to cross this term out. Look, it's moving at 7 meters per second downwards. But remember, if we're ignoring y components, there's certainly no x velocity to this, certainly no x motion to object number 1. Now, object number 2 has a mass of 110 and a velocity of 8 meters per second. It's moving on the x-axis. The combined mass is 200 kilograms. Solve for VF. 110 times 8 is 880, divided by 200 is 4.4 meters per second. Okay, let's deal with the other one now, the y component. Again, pi is equal to pf. By the way, guys, did what we do there, is that any different than what we've done thus far? Probably easier than your quiz questions, right? The quiz that you had today. M1 V1I plus M2 V2I equals MVF. M1, 90 kilograms. What's V1I now? 0? It was 0 before. Same question, isn't it? 0 again? No, V1I isn't 0. When analyzing the x component, ignore y. When analyzing the y component, ignore x. Is that 7 meters per second on the x-axis or the y-axis? Good. M1 is 90 kilograms. V1I is -7. Peyton, why is it -7? Because it's going downwards, right? The first one was +8 because it was going to the right. Second one is -7 because it's going downwards. This is going to be 0, right? V2I is 0 because it's all on the x-axis. And when we're analyzing the y component, we're ignoring everything x. The combined mass is 200 again, times VF. Solve for VF here. 90 times 7, 630 divided by 200 is negative 3.15. What do we got to do after that? Did the x, done that a million times before. Done the y, did that a million times before. Now we got to do what we did a million times back in physics 20. Draw a vector diagram. 4.4, 3.15, and then combine them using the Pythagorean theorem in the inverse tan function. So we're going to say v is equal to the square root of 4.4 squared plus 3.15 squared, and theta is equal to the inverse tan of opposite over adjacent, 3.15 over 4.4. Somebody in the last class asked a really good question. They said, do we need to put the negative in there for the 3.15 now? The answer is no. We have to show direction. We show direction up here by putting a negative sign in. We show direction down here by drawing an arrow downwards. We don't need to show direction in here because this is a Pythagorean theorem. We're putting in magnitudes only, scalars, essentially. Okay, this side of the room, Ben and Over is going to calculate V, and then this side of the room, Haley and Over is going to calculate theta. V is 5.4 meters per second. All right, good. And what is theta over on this side? 36 degrees. Now, how do we express that 36 degrees? Honestly, your diploma exam doesn't use the notation that they've used in this question as far as the angle goes, so we're not going to lose any sleep over that. If you can calculate 36, you're probably fine. But we'll express it this way just because that's the way the book does it. Remember, this is 0, this is 90, this is 180, 270, 360. If this is 360 and this is 36 degrees, then this line right here is 36 degrees shy of 360. In other words, we'd express it as 324 degrees, right? It's 324 past the positive x-axis. Don't lose too much sleep over that. Okay, if you have trouble understanding why that's 324, the biggest thing is recognizing why it's 36. That's the most important thing for us. Yep. No, we will. Yeah, we definitely will. 36 degrees south of east. In this case, it would be 36 degrees south of east. I'm using quotation marks there because it's not really south of east in this case. The reason that they're using this notation, 324 in this case, is because notice what they're saying here. We don't have a north, south, east, west frame of reference. So we're defining 90 degrees as straight ahead of us. That could be north, but that could be west. Does that make sense? So they're saying, look, here's a way to express a direction when you don't know which way is north, if that makes sense. We're not going to have to worry too much about that. We will see the south of east, south of west, and so on. We almost certainly won't see the way that they're expressing that. But it's the way the book uses, so we'll do that. Okay, your homework questions for tonight. Page 492, questions 1 and 2, please. Just a quick little note here. Mac, in question number 2, you see a west and a south, Mac. So that answer is going to be expressed as south of west or whatever, right? That's our frame of reference. For question number 1, we've got 90 degrees and we've got 180 degrees, right? Those are our two directions. All right? Have a good night, guys. We'll see you tomorrow.